Hi friends, this is the heat exchanger part 3. Here now we are going to discuss about the heat exchanger energy analysis. Before going to the energy analysis, we must know why we should do this. In all the energy industries, we have some heat exchanger like energy device. During installation of that thing, we have to know that whether it should be larger in size or smaller should be in size. Or for the application purpose, we should need to predict the outlet temperature or inlet temperature of the fluid. Or we must know that what is the temperature difference between the hot and cold fluid. If we know all these things, then only we can able to design such a application device for the particular power plant or particular industry. As we know, the heat transfer is directly proportional to overall heat transfer coefficient U, then surface area and the delta T. Here the temperature difference between the two fluids, that means hot fluid and cold fluid, it is a driving potential for the heat exchanger. Due to this driving potential, the heat exchanging is taking place. Now we are going to discuss about the notations. Here from after onwards, we are using this type of notations. That means for the hot fluid, we are using the capital T notation, and for the cold fluid, we are using the small t. Here the T1 or TH is the inlet temperature of the hot fluid, and T2 or TC is the outlet temperature of the cold fluid. Here TH is very much greater or very much large when compared to the TC, because during the heat exchanging process the hot fluid loses its heat. Similarly, for the cold fluid, we are using the notation small t1. Here the small t1 and small t2. Here the temperature, if we analyze the temperature, the small t2 is greater when compared to t1, because for the hot fluid at the outlet or the cold fluid is gaining the heat during the heat exchanging process. That means here T2 is greater than T1. That means T2 means at the temperature at the outlet side is greater than inlet side. As per the energy conservation equation, heat gained by the cold fluid should be equal to the heat lost by the hot fluid. As we know, of the enthalpy equation for the open flow system, Q is equal to mCp delta T. Okay, for the heat loss by the hot fluid equal to Q is equal to m dot of H. That means for the mass flow rate for the hot fluid, this is mass flow rate, this is m dot, its unit is kilogram per second, into the specific heat capacity of the hot fluid Cph, the small Cph, into capital T1 minus capital T2. That means the T1 is larger when compared to T2. This is inlet temperature T1 and this is outlet temperature T2 for the hot fluid. Similarly, the heat gained by the cold fluid is equal to Q is equal to m dot into C. M dot the mass flow rate of the cold fluid into specific heat capacity for the cold fluid into delta small t, T2 minus T1. That means outlet temperature minus inlet temperature. Why we go for this means outlet minus inlet. Here the inlet minus outlet. Here the temperature T2 is greater and T1 is lesser when compared to T2. Okay. Here the T2 outlet should be greater when compared to T1. As we know, the total heat transfer Q is equal to U into A into delta Tm. This delta theta m is equal to LMTD. We will discuss it about later. U is the overall heat transfer coefficient, A is the effective area of heat exchanging, and theta is equal to LMTD. LMTD, or we notate this as a Tm of logarithm. This is LMTD. The full form is the logarithmic mean temperature difference. Another one new introductory term is there, logarithmic mean temperature difference. We will go from detail why we go for this logarithmic mean temperature difference. Now we are going to discuss about Now we are going to discuss about the heat transfer in the heat exchanger. Q is equal to UA into T mean. That means logarithmic mean temperature difference LMTD. Okay. We will see why we go for the logarithmic mean temperature difference. Consider for a parallel flow heat exchanger. Okay, parallel flow heat exchanger. Here I am taking a simple shell and tube like heat exchanger. Here this is a tube and this is enclosed in a shell. Here we can able to see this is the inlet side for the cold fluid. This is TC. Here this is the outlet side for the hot fluid TH. Similarly, the hot fluid is circulated around this tube. That means this is a flow path for the hot fluid. This is a capital TH and this is a capital TC. This is a parallel flow heat exchanger. Parallel flow heat exchanger. This is a case for the parallel flow heat exchanger. Now we are going to detail about what is meant by LMTD, logarithmic mean temperature difference. For parallel flow heat exchanger, here I am going to draw a graph for the heat exchanger and for the temperature as well as along the length. This is the length. Here this is the inlet side 1 and this is the outlet side 2. The length goes on increasing from 1 to 2. This is the total length. 1 to 2 is the total length of the heat exchanger. Okay. Now, in the y-axis, this is the temperature. For the temperature. Now, we are going to detail about the hot fluid and cold fluid separately. First, we are going to analyze about the temperature of the hot fluid. As we know, at the inlet side, for the parallel flow heat exchanger, at the inlet side, the temperature of the hot fluid will be more when compared to the outlet side. Hence, this is the maximum temperature TH. Okay, TH. And here, somewhere here, the TC will be there because the temperature is getting on decreasing throughout the length. Hence, the graph will be like so. That means during the flow from left to right, the temperature goes on decreasing. Similarly, in case for the cold fluid, the inlet temperature of the cold fluid should be very low. That means somewhere here, small TC. And if the cold fluid flows along through this length, the temperature goes on increasing because the heat exchanging takes place from the hot fluid to cold fluid. Hence, the graph will look like so. Here you can see the direction. The both fluids are traveling in a same direction and the both fluids are ended in the same side too. That is a parallel flow heat exchanger. Now we are going to analyze that one. Suppose here at the inlet side you can able to see what is a temperature difference. That means suppose if I am taking this as a particular instance or particular position of a heat exchanger, here you can able to see at this inlet side what is the delta T, what is the temperature difference. For analyzing the temperature difference, that means high temperature of the hot fluid and the low temperature of the cold fluid. That means now the temperature difference is delta T. This is the delta T at inlet. Okay. Now, what is the temperature at the outlet side? At the same, at in another position, what is the temperature at the outlet side? Delta T at the outlet side. Here, this is a small t h. Okay. Now, this is a delta T. Here you can see delta T outlet. Here the delta T1I and delta T O. Here you can see it look like so. If length goes on increasing, here at the inlet side delta t is more. Delta t is more. If the length goes on increasing, delta t gradually varies. Like so. That means here the temperature difference is not constant. It should be some varying like in nature. But for our analysis, we need a mean temperature difference. For that purpose, we are going for the logarithmic mean temperature difference formula. After calculating this logarithmic mean temperature difference, we will get a mean temperature difference between the hot fluid and cold fluid at a particular area. After calculating this logarithmic mean temperature, our LMTD temperature will be like so. This is our LMTD. LMTD. Now this temperature, delta temperature is constant. Now we can easily able to calculate in our calculation, used for our calculation. For that purpose, we are go for the logarithmic mean temperature difference. Here you can see the logarithmic mean temperature difference, LMTD, is defined as the temperature difference which, if it constant, would give the same rate of heat transfer as actually occurs. Actually, after calculating the LMTD, the temperature is a constant, delta Tm is constant. Before that, it is a varying nature. That means, as a graph indicates, this delta T is varying in nature. As actually occurs, actually means varying nature under the variable condition of temperature difference. For calculating this logarithmic mean temperature difference, we must have do some assumptions. That means, first of all, the overall heat transfer is the constant one. Then, under the steady state condition, the equation is only validated. And here the CPH, the specific heat of the hot fluid and the specific heat of the cold fluid should be the same. That means the value should be the same. And the mass flow should be same. That means suppose 10 kilogram of the hot fluid is passing through the shell, and similarly the 10 kilogram should flow over the tube also for the cold. And no changes in the kinetic energy and potential energy. That means the potential here, the potential energy and kinetic energy should be negligible. And another one is the axial heat conduction is negligible in nature. By assuming all these conditions, we are going to derive some logarithmic, what is a logarithmic mean temperature difference for the parallel flow heat exchanger. Suppose I am considering an area dA for this heat exchanger. Here, this is a particular area. That means here I am going to calculate about this instant. Okay, this is the dA. I am going to calculate about the heat transfer at this particular area only. Okay, that means first of all I am just pointing out this area. Then after that I am going to integrate from 1 to 2 or from inlet end to outlet end. Then I will get the total heat rate. This is a dA. Now I am going to calculate, this is the delta T for a particular area. This is the delta T. And in case of the hot fluid, this is the temperature difference in this particular area. This is the temperature difference. This is a D capital T. Okay. And for in case of the hot fluid, cold fluid, this is the delta change in temperature along this particular length of the dl. Okay, this is the small dt, small t, and this is a capital T for the hot fluid and for cold fluid. And this is a delta T, and this is the at a length is equal to 0, at x is equal to 0, and here the length is equal to L, x is equal to L. Now we are going to discuss about this is a T outer or T2, this is a T inner or T1. Okay. Now we are going to discuss about this parallel flow heat exchanger, LMTD for the parallel flow heat exchanger. As we know, delta Q is equal to U into dA into, that means for a particular area, that means del Q into U into dA into TH minus TC or delta T. At the particular constant, here this is a TH and here this is TC. This is a delta T. By energy balance equation, we can know that del Q is equal to for the hot fluid and del Q for the cold fluid. As by energy balance equation, both the Q heat transfer should be more or less same. Del Q is equal to minus m dot h, that means the mass flow rate of the hot fluid into specific heat capacity of the hot fluid into delta TH, that means this dt. Okay, this dt. Minus indicates the heat is going from the particular body. That means heat is given out from the system. That means this is minus. Similarly, for the cold fluid, mass flow rate for the cold fluid into specific heat capacity of the cold fluid into delta Tc. This is the delta Tc, this is delta Th. Okay. Now, from this equation, what is delta Th is equal to minus dq by m dot h into Cp of h. Similarly, equal to this m dot h into Cp. This m dot h into Cp, we can write it as capital Ch. This is the total heat capacity, capital Ch minus del Q by capital Ch. Similarly, for delta Tc, del Q divided by capital Cc. Total heat capacity for the cold fluid. Now, as we know, Q is equal to UA into delta T. We are going to calculate what is this term. Okay, now we need to find out this term. For calculating this term, we are going to calculate about this particular area, differentiate about the particular area. Okay, dA, particular dA. Hence, what is a d delta T equal to dt minus dt. That means d capital T minus different temperature of the small t. That means here minus this. From this equation, from dt, what is meant by dt? Dt is equal to, as we know, the dth is equal to minus dq by ch, and small dt is equal to minus del q by cc is equal to del q by ch minus del q by cc. Del q is a common one, common factor, hence we arrange the equation like so. Finally, we will get what is del q is equal to minus ua delta t. That means finally we will get ua into delta t to 1 by ch plus 1 by cc. This is for the particular area or particular instance. For the particular instance. Now we need to calculate the heat exchange over the entire length from 0 to 1 or 1 to inlet to outlet, 1 to 2. Okay. For that purpose, we are going to integrating this equation by using variable separable form. Integral over the length T1 to T2, that means inlet to outlet, over the temperature delta T, and this T comes to here, and delta T by delta T is equal to minus U into 1 by Ch plus 1 by Cc. Here only the variable area is, this is also here, this is dA, and another one dA is here. Only variable term is the area. Area means length of that heat exchanger. Now, as we know, dx by x is equal to ln. Now we know ln delta T2 by delta T1 equal to minus U into area. Area 1 minus area 2 means total area. Area into 1 by Ch plus 1 by Cc. Now, ln delta T2 by delta T1 is equal to UA into 1 by CH plus 1 by CC. We can able to write this 1 by CH equal to capital CH equal to, as we know, CH is equal to del Q by minus del Q by TH minus TC. That means delta TH. Capital TH minus capital. Similarly, 1 by CC equal to del Q by small TH minus small TC. Okay. Here we are going to substitute for this term. Minus UA into TH minus TC plus TH minus TC. By rearranging we will get TH and TH. TH and TC, and this TC and this TH. You will get TH minus TC minus TC minus TH. Here you will get minus UA by Q delta T1 minus delta T2. This is input side, or this is outlet side. From the graph we can able to see. This is a capital TH, this is a small tc. Here the capital TH minus small tc. This is a input side. This is a delta T1 minus delta T2 is equal to, here capital TC minus capital T small th minus small th. This is delta T outside. Now what is the heat difference? The heat transfer is equal to Q is equal to UA into delta T1 minus delta T2 divided by ln delta T2 by ln delta T. Now this term is the logarithmic LMTD for parallel heat exchanger. This is a similarly notation what we have to in our data book too. That's why I go for the 2 and 1. In some other text it is indicated as HC and all these things, but as of now concerned, the data book's notation is better for our solving the problems. Okay, thank you. Next session we are going to discuss about what is the LMTD for counterflow heat exchanger. Thank you.